Hey you guys, today we're going to be working on section 3.2, motion with constant acceleration. All right, so to start out, let's look at a car, okay? The car is going to start out with an initial velocity of 10 meters per second at time t equals 0 seconds. So at the time 0 seconds, the car is going to be going 10 meters per second. 1 second is going to pass, and after 1 second passes, the car is going to be going 15 meters per second. So at time 1, which is 1 second, our velocity 1 is going to be equal to 15 meters per second. Go a little bit further. Now we have v with the subscript 2 is going to be equal to 20 meters per second, and our time is going to be equal to 2 seconds. So each second, you'll notice our velocity is increasing by 5 meters per second. We go 10, 15, 20. So if we go 10, 15, 20, that means that our acceleration is equal to 5 meters per second squared. So we actually have an equation that we can use to get that. If maybe the numbers aren't exactly, spaced apart, maybe they're like a weird decimal or fraction or something, or with whole numbers, there is an equation we can plug this into. That equation is going to be that VF is equal to V naught plus AT. So our final velocity is equal to our initial velocity plus our acceleration times our time. So if we want to solve that for this, let's say we want to double check with this velocity 2 right here. Let's say we want to check that. We would put in that our final velocity is equal to our initial velocity, which is 10 meters per second, plus our acceleration, which is 5 meters per second squared, times our time, which is 2 seconds. And if we do that, we get a final velocity of 20 meters per second. Okay? So that's going to show that this equation does work. Now remember, this equation can be used to solve for any of the variables. We can use it to solve for our final velocity, an initial velocity, an acceleration, or a time based off of what variables we're given with at the start and what we're asked to find at the end. Okay, all right. What we're gonna look at now is another example of what is the velocity. So let's say we have a baseball, and what we're gonna do is we're gonna throw it upwards. So I'll use this little pack of sticky notes, okay? So we're gonna throw it up, and what up goes up must come down, right? So we'll throw it upwards with an initial velocity. So our V naught is going to be 8.2 meters per second, okay? Gravity, which is what holds us down to the ground, right? Gravity gives the ball a downward acceleration. And the downward acceleration that gravity gives the ball is that acceleration is equal to negative 9.8 meters per second squared. So negative 9.8 meters per second squared is going to be the acceleration on the ball after it's getting pulled down. So what we want to know is the velocity of the ball after 1.5 seconds. So our time is going to be 1.5 seconds, and what we want to know is the final velocity. So we'll use our equation that we just learned, that our final velocity is equal to our initial velocity plus our acceleration times our time. When we plug in our values, we know that our initial velocity is 8.2 meters per second, plus our acceleration, which we were told is negative 9.8 meters per second squared, times our time, which is going to be 1.5 seconds. All right, type that into your calculator and see what you get. Okay, hopefully when you typed it in, you got an answer of negative 6.5 meters per second. Okay, now why that's negative is because when I took my sticky notes and I threw them up with maybe a velocity of 8.2 meters per second. And then they come down. Now on the way down, the direction has changed. So on the way up, it was a positive velocity of maybe 8.2, but once it reaches the top, the velocity is at 0, and then it starts to come back down. And as it's coming down, the direction changed, and now down is considered the negative direction because up was the positive direction. Does that make sense to everybody? I hope so. All right. So there was another example. Now let's look at how to get average velocity when acceleration is constant. So an average velocity. So we've talked a lot about constant velocities, right? And that means that the velocity isn't changing. But now since we have acceleration, literally the definition of acceleration is that the velocity is changing over time. So I've got a graph for us to look at, okay? Let's look at this velocity versus time graph. Our time and our velocity are both going to go from 0 to 5. And what it looks like is that every 1 second, we're going to increase by a meter. So at time t equals 0, we're going to be at 0 meters. At time t equals 1, we'll be at 1 meter. Then at t equals 2, we'll be at 2 meters. Then at 3 meters. Then at 4 meters. Then at 5 meters, and so on and so forth. And it'll end up giving us this really nice linear progression, okay? And what we want to know, though, is what is maybe the velocity right here or right here. So like at 0.5 seconds or at 1.5 seconds. Well, at 1.5 seconds, we're going to have an average velocity of 1.5 meters per second, and at 0.5 seconds, we're going to have an average velocity of 0.5 meters per second. Okay? But like with everything, there's actually an equation to use to check that this information is accurate. Our equation for average velocity is that our average velocity is equal to 1/2 v naught plus v final. So our average velocity is equal to 1/2 our initial velocity plus our final velocity. So let's plug in this information and see if we can get the right answer, okay? So let's start by looking at 0.5 seconds. So we would have 1/2 our v naught would be 0, our VF would be 1. So we're looking for the average velocity from 0 to 1, all right? Our average velocity from 0 to 1 is going to be 1/2 0 plus 1, which equals 0.5 meters per second, just like we said. So if we want to find our average velocity between maybe 1 and 2, we're going to have 1/2 1 plus 2, and that's going to give us an average velocity of 1.5 meters per second, like I said we have. Okay, so this is our equation for average velocity. Our average velocity is equal to 1/2 of the initial velocity plus the final velocity. So if we wanted to find the average velocity even between maybe 1 and 3, between 1 meter per second and 3 meters per second, we could do 1/2 1 plus 3, and we're going to get that the average velocity is equal to 2 meters per second between 1 and 3. And it is right here, going to be equal to 2 meters per second. So you could use this equation to find the average velocity of any point on this graph. So you guys remember learning our equation of motion? Remember how we learned that it was x final is equal to x initial plus vt. So our final position is equal to our initial position plus our velocity times time. And when we learned that, we only knew constant velocity. We didn't know about average velocity yet. So you can actually use this in the average velocity equation. How we do it is we are going to sub in, you know how we had V average is equal to 1/2 V naught plus VF. We're going to take this and we're going to plug it in for our V here. So what happens to our equation is we end up with our final position is equal to our initial position plus 1/2 of our initial velocity plus our final velocity times t. Okay? So now this is getting solved using an average velocity. Here it's with a constant velocity, here it's with our average velocity. So let's look at an example, okay? All right, so in this example, we'd have a boat and it's slowly moving inside a marina and it has a speed of 1.50 meters per second. And as soon as it leaves the marina, it's going to throttle up. So it's going to start going faster and faster and faster. And when it throttles up, it has a constant acceleration of 2.40 meters per second squared. And you'll notice since it's throttling up, that means the acceleration is working with the velocity to push it further in the direction that it's already going. So our acceleration is positive, just like our velocity is. So we want to know two things. The first thing we want to know is what is the velocity of the boat after accelerating for 5 seconds. So let's put t equals 5 seconds, and we want to know what the velocity is at that t equals 5 seconds. So what we can use to find this is the equation that we just learned, right? Our VF equals V naught plus AT. The good news is that we don't have to do any rearranging for this. We're looking for VF, which is what it's already set equal to, and we have V naught, A, and T. So all we have to do is plug it in, okay, you guys? So for V naught, we're going to plug in 1.5 meters per second, all right, plus 2.4 meters per second squared times 5 seconds, all right? So type that into your calculator. 1.5 meters per second plus 2.4 meters per second squared times 5 seconds. And what do you get? All right, I hope that you got 13.5 meters per second, okay? It's going to be 13.5 meters per second. That's how fast the boat will be going after 5 seconds. Okay, so that was the first thing we wanted to find. The second thing we want to find is how far the boat travels in this time. So now we want to know what our displacement is. We want to know delta x, okay? How we're going to find that is using another equation that we just discovered, okay? We are going to use that final position is equal to initial position plus 1/2 V naught plus VF T, okay? Remember, that's how we just rearranged the equation of motion to use an average velocity. So all we have to do here is plug stuff in again, all right? So if we're looking for our delta x, and delta x is final minus initial, and we're not told an initial position, we can usually assume that the initial position must be 0 meters, which means that our initial position is 0, which means that currently delta x is equal to xf. So we just said that our initial position is 0, so that's going to go to 0. And now we can plug in our terms. So we're going to have that our final position is equal to 1/2 1.5 meters per second plus that 13.5 we just found plus 13.5 meters per second times 5 seconds. So we have our final position is equal to 1/2 1.5 meters per second plus 13.5 meters per second times 5. So I want you to go ahead and type that into your calculator and see what you get. All right, what you should have gotten is 37.5 meters. Okay, that's how far the boat's traveling in that 5-second time frame. It's going to travel 37.5 meters. All right, now we're going to look at how we can find position from a velocity versus time graph. Okay, so this is the graph that we have. We're going to have time on that x-axis like we usually do, and we're going to have our velocity on our y-axis like we usually do, okay? We're going to have speeds 1.5 and 13.5, and then our times are going to be 0 seconds and 5 seconds. So our speeds should be labeled 1.5 and 13.5, and our times should be 0 and 5, okay? At 0 seconds, we're going to be at 1.5 meters per second, and at 5 seconds, we are going to be at 13.5 meters per second. So once again, this is going to create a really nice linear graph for us. Now we're given this, and we are personally asked to find the position of this object. We're told that at t time equals 0, that x naught is equal to 0. So it's starting off at 0, okay? So we don't need to worry about adding on any initial positions at any point. It's at 0. How we find the position from a velocity versus time graph is it's actually going to be this area under the curve. Now what's great about this is you can actually split these up to 2 areas that we know how to find. We're going to have the pink area and then the blue area, okay? The pink area is going to be the area of a rectangle, and the blue area is going to be the area of a triangle. So if we start out with the rectangle, we know how to find the area of a rectangle. It's length times width, right? So its length is going to be 5 seconds, and its width is going to be 1.5 meters per second. So what do you get when you do 5 times 1.5? Hopefully you get 7.5. And those seconds cancel to leave you with meters. So you should have gotten 7.5 meters for the area of your rectangle. So now we need to look at our triangle. What is the equation for the area of a triangle? It's 1/2 base times height, right? Okay, so 1/2, our base is once again going to be 5 seconds. And our height is going to be from 1.5 to 13.5. So we can do 13.5 meters per second minus 1.5 meters per second. Okay. When you enter that, what do you get? 1/2 times 5 times 13.5 minus 1.5. Hopefully you are coming up with 30 meters, okay? So we know that the rectangle has an area of 7.5 meters and the triangle has an area of 30 meters. So what we're gonna do to find out the position at 5 seconds is we need to add these two together. So we're gonna do 30 plus 7.5, all right? 30 plus 7.5. And when we do that, what do we get? We should get 37.5 meters. So at time t equals 5, on this velocity versus time graph, our object is at position 37.5 meters from its starting point of 0. Okay? So how we find position from a velocity versus time graph is by solving the area under the curve. So the area under the curve gives us our position. Okay, so the next thing to think about is that we just talked about how to find position from a velocity versus time graph, but position is also related to our main topic of acceleration, okay? So position is related to acceleration and time. We just learned that our final position is equal to our initial position plus 1/2 initial velocity plus final velocity times t, and that VF is equal to V naught plus AT. So what we can do, your guys' absolute favorite thing, is that we can take this right here, this V naught plus AT, and we can plug it in for the VF in this equation. And it's going to give us a brand new equation. So watch what happens. Now we'll have our final position is equal to our initial position plus 1/2 V naught plus V naught plus AT times t. Okay? And from there, we can simplify down and get that our final position is equal to our initial position plus our initial velocity times t plus 1/2 AT squared. Okay? This right here is the equation that you need to know, okay? I do not care if you know how we got there. What I care is that you know that your final position is equal to your initial position plus your initial velocity times your time plus 1/2 your acceleration times your time squared. This is going to be one of our kinematic equations, okay? So now that we have that, let's use it. All right. Put the pedal to the metal, but not really because then you're speeding. So I've heard that we have a few fans of Tesla Roadsters throughout my classes. So we're going to have a Tesla Roadster. I'm not going to try and draw that, but it's going to start from rest. And since it starts from rest, that means that we know the initial velocity is 0 meters per second, okay? And it accelerates at 7.4 meters per second squared. 7.4 meters per second squared. All right, we want to know how far it will travel in 1 second, 2 seconds, and 3 seconds. So we're looking for how far. Okay. Well, we just learned a new equation, right? We learned that our final position is equal to our initial position plus our initial velocity times t plus 1/2 at squared. All right, well, it didn't tell us where we started from, which means that our initial position is also 0 meters. So we can get rid of a few things in this equation and not have to worry about them anymore, okay? X naught is 0, so we don't have to worry about it. V naught is 0, so if you times it by t, that whole term goes to 0, which means that we're left over with our final position is equal to 1/2 our acceleration times our time squared. So now we just need to plug in our numbers for 1, 2, and 3 seconds. So what we're going to get is 1/2 7.4 1 squared, 1/2 7.4 2 squared, and 1/2 times 7.4 times 3 squared, okay? So if you take a moment to type those in, you should get that at 1 second, we are at position 3.70 meters. At 2 seconds, we are at position 14.8 meters. And at 3 seconds, we are at position 33.3 meters, okay? So at 1 second, 3.70 meters, then 17.8 meters, and then 33.3 meters.